thanks for giving me the opportunity to describe a work we did with the collaborators that are listed here on actually small scales, dwarf galaxy formation, which is small, and then large scale, mainly elliptical galaxy formation or BCG. And so I will very briefly first describe why feedback is so important in galaxy formation. And then I will describe the two pieces of work I want to report on. The first one is a recent paper that was posted on the archive about the simulation of an isolated dwarf, so it's not a cosmological simulation, with a stellar feedback and what are the consequences, the observational consequences that we can draw out of this simulation. And then the second part will be dedicated to the work done by Davide Martizzi in Zurich on the formation of massive ellipticals, and of course of the role of AGN feedback. So galaxy formation is of course a hopefully complicated process, but just to simplify the context, I want to show this plot here, which is the so-called abundance matching plot, which shows that the stellar fraction divided by the stellar mass of the central galaxy, divided by the halo mass, the host halo mass, has this typical bell-shaped curve, which peaks at the Milky Way scale, and then goes down on the left and on the right. And so here it's clearly a manifestation that the star formation efficiency, the efficiency of converting baryons into stars, declines to low mass and also declines to large mass. And so in order to understand galaxy formation, we need to reproduce, of course, this curve, this so-called abundance matching curve, and that's the tricky thing we all work on. So it was proposed by Deckel and Silk, of course, to explain this low efficiency on small scale by stellar feedback, and more precisely supernovae feedback. And actually, Avishai just told me yesterday that he wrote this paper when he was in Caltech, I think, after spending 2 months looking at photographic plates, believe it or not. And then, he was exhausted, and then he wrote this paper. That's what you told me, right? So that's an interesting story. So here, of course, that's the first part of my talk today. We'll focus on dwarf galaxy formation here. And then, of course, to explain why star formation is so inefficient at a large scale for large halo mass, it was proposed, among many others, that AGN feedback might play a role here. And that's what we're going to address in the second part. So just to comment again on why feedback is so efficient in a galaxy formation. So this is again a plot extracted from the Aquila comparison project from Cecilia Scanapico et al. And what is plotted here is again the same abundance matching plot, if you want, where you have the halo mass and the stellar mass. And abundance matching gives you this gray area. So this is basically the target that we want to get. Of course, the point here to make is that you have a dispersion in the observation. So we don't want all galaxies to sit at the average, right? We want to reproduce the dispersion, which is also tricky. But here in this comparison project, you see all those codes, and the dispersion is quite high. You can have actually a very high stellar to halo mass ratio here for those actually free simulations, which are all obtained with a mesh code, namely Arepo and Ramses here, with very inefficient feedback, all the way down to a simulation with a very strong feedback. So here you have 2 simulations with AGN feedback here, and 1 simulation with a very strong stellar wind implementation. And so here the point to take away is that bulk galaxy properties, like the total stellar mass, depends directly on feedback. So cosmology, of course, plays a role, but it plays, I think, a weak role, especially if you, in light of these results. And when you look at more detailed properties of galaxies, such as the morphology, whether it's a disk or a spheroid, it's even stronger. And actually, one conclusion that we get from this work was that all the galaxies with very high star formation efficiency looked like nice disks, but with way too many stars. And all the galaxies that kind of matched the correct star to halo fraction ended up being spheroid, with a very weak, if any, disk component. So this is a big problem. There are also numerical problems to be solved. Here you see all the grid-based code with weak feedback giving you a star formation efficiency which is lie at the high end. while SPH code, with again very weak feedback, tends to give you something which is a factor of 2 lower. So besides feedback, there are also some numerical issues to be understood. Okay, so first...
Sorry, Romain, your point there was that you can always boost feedback in order to decrease the star formation efficiency, but then you destroy the disk.
In this particular case, that's what you get, right? The price to pay to get the correct baryon fraction in star is to destroy the disk. And the reason is that feedback is very efficient, but it's also very efficient, so it basically kills star formation at late time. And regulate at early time, but completely kill at late time. And so you don't want that. You want star formation to be almost constant. Low, very weak, but constant. And none of those simulations reproduce this result, with all the caveats that Joe mentioned. Okay, so now briefly I will mention the work we did on this dwarf galaxy simulation. So dwarf galaxies are governed, we think, by stellar feedback. But even the good old supernova feedback is very tricky to implement. I think we will discuss this afternoon more realistic implementation of stellar feedback, hopefully. Here, I'm presenting you very briefly, I don't have time to go into details, what we did recently in Ramses to implement stellar feedback using a non-thermal energy approach. Basically, in a nutshell, thermal energy, when you inject thermal energy is dissipated on a time scale which is given by the cooling time, which is very short. So you probably want to consider other sources of energy, like kinetic energy in turbulence, or cosmic ray energy, or magnetic energy, or whatever. And all those energies dissipate less efficiently on different time scales, which are also very complicated to compute. So here we decided to go into a simplified kind of approach, where you inject this non-thermal energy, and you just consider the dissipation time as a free parameter. And so here what we considered is that most of the supernova energy, actually all of the available supernova energy is given into this non-thermal component, and that this non-thermal component dissipates with a fixed time scale, which is chosen to be 10 million years. Of course, you have plenty of more sophisticated models you can play with. But at least what we obtain here, and I think that's very important in the stellar feedback recipes we all use, we obtain the qualitative effect that dense clumps that form inside the disks are destroyed after a few million years. And that's basically what we want to aim in terms of feedback, main feedback property. So we applied this new feedback recipe to a simulation of an isolated dwarf galaxy. So just to give you very briefly the context, it was shown recently by the gasoline people that, and earlier work by Justin, that in order to reproduce a very striking property of dark matter halo at the scale of dwarf galaxies, namely the formation of a core, you can get this using baryonic physics with very strong feedback mediated by the formation of these dense clumps. And so this was shown first by Mashenko et al., and then more recently by Governato et al. And then the process of core formation was, I think, nicely explained or discussed by Andrew Ponsen by invoking gas mass fluctuation, which trigger the formation of this core, which heat up the dark matter. So what we did was to run this simulation using an isolated equilibrium NFW halo. And so to check that our setup is consistent, we run an adiabatic simulation over 2 gigayear, and checking that this was indeed completely stable, both in the gas and the dark matter component. Then we run a second case with only cooling and star formation. And as time progresses, basically in this plot showing the dark matter density profile as a function of radius, we see that we have a very strong adiabatic contraction of the dark matter due to the formation of a very dense stellar disk. And then we run the same simulation, this time with this new stellar feedback implementation. And so just to give you a visual impression of the result, so this is what we obtain after 2 gigayear of evolution. So within the central 10 kpc here, we see the disk edge on and face on. In the no feedback case, so you have a very thin, clumpy disk with a lot of stars, actually way too many stars, and you see very long-lived star cluster here that actually are orbiting around. While in the feedback case, you have a completely different result. You have a very violently turbulent disk here, which is very thick. So this is side on. This is a side on view, right? and this is the face-on view, and you see this hole here, which is typical of this kind of simulation, where you evacuate the gas mass in the inner region, where the star formation is stronger, and then you see this very low surface brightness galaxy here, in terms of star distribution here, where the star formation efficiency has been dramatically decreased. So now if you look at the dark matter core actually formation, you do see the formation of a dark matter core. It's a striking difference with the previous simulation we did without feedback. And the interesting thing is that this core is very well fitted by a pseudo-isothermal law like that. And the core size is growing slowly, steadily with time. So we basically came up with the same conclusion as Andrew was proposing, namely that because of this bursty star formation rate that we have in this dwarf galaxy, we push gas around, and you end up with very strong gas mass fluctuation at different scales. And actually the core size that you get in the end correspond to the scale for which those potential fluctuations are of the order of 50%. And so that's how you determine the size of the core in this picture. It's the scale within which you get 50% of mass fluctuation inside the sphere. So now, so this is again a plot showing the evolution of the slope, and you see that you have a systematic, irreversible flattening of the cusp into something which is much flatter. And this is in complete line with what was found with gasoline and the cosmological simulation at lower resolution. So now one interesting consequence beside the core formation is that you get this very thick galaxy with a very extended stellar distribution. And actually there is a very good example in the nearby universe, which is the WLM dwarf, which was for which the recent observations are discussed in this paper here. And you see that this is an image almost side-on of this galaxy. So WM is interesting because it's an isolated dwarf which is very, which is believed to be, outside the Milky Way halo, or just coming in for the first time. So not being subjected to tidal effect or ramp pressure effect. So it's a good isolated dwarf candidate. And you see that it resembles very well our simulated galaxy. When you look in more details, you see that the total stellar distribution in this galaxy has a typical exponential disk plus a core here. And the disk scale rate is 1 kpc. And in our case, with feedback, this is a red line, we also get the chord exponential with an exponential disk. And so, okay, I'm going to skip here a bit. So the mass profile of WLM was determined using some feeding function here, either NFW or singular isothermal spheres. And then this paper was used to determine the halo mass, which is 10 to the 10. And you can see here the stellar mass that is observed in this galaxy, which is 10 to the 7. And it fits nicely into the abundance matching constraint from Guyot et al. The problem we have in our simulation, and that's the big caveat here of this study, is that in order to get this effect of core formation, and we used a standard recipe for the star formation efficiency, we actually form 10 to the 8 solar mass of star within 1 kpc here. So we are basically 1 order of magnitude above the constraint from observation. So it means we need too many star formation yet, although it's been reduced by 1 order of magnitude compared to the no feedback case, but we still 1 order of magnitude above. So it means in order to really fit all observational constraints, we need to form 10 times less star, but with the same feedback energy. And so we have a problem, right? So one way to go is to invoke actually more efficient stellar feedback recipes. It's completely possible, right? To have a higher efficiency in the coupling between the energy of the supernovae and the energy of the wind. That's one way to go. The other way to go is to invoke both a lower star formation efficiency, because, for example, you work at low metallicity, and a top-heavy IMF, so that you restore the energy that you lose by forming less star. So that's one other solution. But here you see that the picture is pretty nice, and we have a lot of interesting observational consequences of this simulation, but we still have this problem of forming too many stars.
Can you show the previous plot? So in the previous plot? No.
I'm sorry.
Okay, so that shows that,
That's
you have the right total stellar mass.
no, that's the observed galaxy. That's the observed galaxy. Our galaxy is up here. It's at 10 to the 8.
So it's not just the distribution of stars, it's the overall stellar content.
The overall stellar content is too large. So actually, that's what I'm plotting here again in this plot. So our galaxy is here, right? That's the pink point here. So we are grazing the the 3 sigma region for abundance form.
If I can keep interrupting.
Go ahead.
That's the old abundance matching plot. The new one, which I think Peter was showing, on dwarf galaxy scale, shows a flattening. So you might be too high compared to Monster, but I think you're probably...
Actually, the Monster is really low, so I think it's fine.
Okay, interesting. But then WLM is not. So then, okay, but WLM might be a.
The other problem is that
Sorry.
it seems to be the general fact that for these low mass galaxies, abundance matching doesn't work very well.
No, I agree.
Lower masses, but I think
this is on the edge where it should work pretty
Exactly.
If you take that plot from the latest paper by Peter, you'll see that the star formation efficiency will flatten
Okay, but
at low masses.
But at lower mass or at this
No,
mass?
there.
I think it's 1 sigma, because I get the same stellar mass with my simulation, and I put it on Peter's new plot, and it's 1 sigma away.
So
Okay.
I should caution that these 1 sigma intervals are not real 1 sigma intervals.
So this is.
You've got a good observation system.
No, yeah. So,
I think the point is those are basic points that the observed snow masses tip up at low masses.
okay.
That's what causes a deflection of low masses of this
Okay.
The parameterization of the bit is that will power level, so not flexible enough to include this alternative masses.
So maybe you're okay. That's the
Okay, but I think.
all of this with it.
Okay. Okay, great.
What is the stellar mass for that galaxy? You don't need to know. Is that what to know?
That's the stellar mass of the observed galaxy, WLM. It's 10 to the 7.
So doesn't that
And the stellar mass I obtain with my simulation is 10 to the 8. So I am 1 order of magnitude above this galaxy. But maybe this galaxy is low compared to abundance matching, and my galaxy is high, right? But
abundance matching on that scale is very uncertain. That's what you have to constantly say last one.
but if I want to reproduce the WLM observations, I have to boost the feedback while lowering the star formation efficiency. Right. That's clear.
It's still possible that WLM is extended more surface mountains. There are some dwarfs where people have found more stars as long as they go to the low surface brightness.
No, of course. So that's the other issue, right? Is that all those points are measured within 3 kpc, right? And the halo size is more like 30 kpc. So you extrapolate, of course, this mass profile up to 30 kpc, and maybe that's the problem. And then you know, that's the other point. Maybe the total halo mass is smaller. Okay, now I have 2 minutes to discuss the other part of my talk, which is the large scales. So just to show you a few examples of galaxy formation simulation spanning the mass range that Joel was mentioning, from 10 to the 10 to 10 to the 13. And you see that Eris is sitting here, pretty good, close to the average of the abundance matching plot. The Aquila comparison project with Ramses is sitting up here, so the one without AGN feedback. So way too many stars, right, in this case. And if you use AGN feedback, you go down to you know, where you should be, except you don't have a disk anymore. Right? So now when you move to very large galaxies, and that's what I'm going to do in my last minute here, or 2 or 3, is that you are really in trouble if you don't include AGN feedback. And so actually this is easy. This is all very easy. Right? What is very complicated is to form massive ellipticals. And then if you don't include AGN feedback, then you're out there. So you have just crazy galaxies that just don't exist anywhere. Right? Then with AGN feedback, I will present the result quickly, you go down into something much more reasonable. So I will briefly skip this part, which is the AGN feedback model we're using is a very classical model. It's the Booth and Shai model. So if you have questions how we implemented this in Ramses, I mean, I'm ready to tell you the secrets here. So just this image to show that you have the star distribution in this Virgo-like cluster, the gas distribution, and the dark matter distribution without AGN feedback. So you have a huge galaxy in the middle, galaxy that you can find nowhere in the universe. And then the bottom row, you see the same simulation, the same halo, but run with AGN feedback. And you see you have much less star here. The gas is also much less clumpy. You have more gas in an extended halo. And also the dark matter halo has been modified. You have a much rounder halo here, and here it's more like a dark matter only simulation with an oblate halo. So you change the dark matter, sorry, you can modify the byte central galaxy property drastically in this size velocity dispersion and size stellar mass plot. So the first galaxy without AGN feedback was out there, completely outside the existing galaxies we observe. And then when you put AGN feedback, this galaxy goes back into what real galaxies look like. So just to briefly comment on the last point I want to make here, is that those early type galaxies has been observed, since ever. And there is an interesting dichotomy that we can see here in the surface brightness profile of those galaxies, is that large galaxies usually show in the surface brightness those very nice extended cores, while smaller galaxies show power laws or cuspy profile, right? And this, actually you can see that the cores here are, for the largest one, are for the order of one or few kpc, but the typical size of those cores is more like half a kpc, right? So just to give you another example of, from a paper by Corbin et al. So this is a small mass elliptical galaxy where you see this cuspy profile in the center, which actually you have an excess of light compared to the Vaucouleurs. And then the large ellipticals, which show very well-defined cores, for which the size goes from half a kpc for this one, up to 3 kpc in the case of M87. And so here you don't really have a core, you have like a broken power law. So what is interesting, and I will jump to the conclusion here, is that in our simulation with and without feedback, we actually reproduce this dichotomy. Without AGN feedback, we see no core, we see a cuspy profile with a light excess. But with AGN feedback, we see a pronounced core, okay, a bit too big, 6 kpc, so we probably overdid it a bit. But you clearly see a core and way above the resolution limit of the simulation. And so just to conclude, we actually explain that this core, the traditional mechanism for core formation in massive elliptical is due to black hole scoring. So you have the AGN black holes that are coming together with the host and satellite galaxy, and they orbit around, and with dynamical friction, you just evacuate the stellar component. And what is interesting here is that we see the formation of a core both in the dark matter and a broken power law in the stellar component at very high redshift already. And very high redshift means the black hole mass is very small. So you can't use black hole scoring to explain what's happening here. And so what we actually have found here is that the core formation mechanism is probably much closer at high redshift to what's happening for dwarf galaxies. Namely that you have massive gas mass fluctuation within a radius of several kpc that you can see here in the simulation, which at high redshift are really striking and which explain, based on the same theoretical explanation than for dwarf galaxies, why you evacuate the dark matter particle from the center. And that would be my conclusion. Basically that on small scales, feedback effects are very important in shaping the galaxy and, of course, providing the explanation for a dark matter core. But also on large scale, this time AGN feedback, sometimes with mechanism very close to what's happening on small scales, also have a very important role in shaping the dark matter distribution and the baryon distribution in massive ellipticals. Thank you.
Thank you.